Hello, this is question 2 of the 2010 MAT. So this is for all applicants. Suppose that A, B, C are integers, such that that equation holds. By squaring both sides of the equation, show that A equals B equals C equals 0. And we assume that root 2, root 3 and square root 2/3 are all irrational. Rational number is one which cannot be written in the form P over Q, where P and Q are integers. Okay, well, I'm not too sure how that's going to work out, but they've told us how to start. Square both sides, so let's square both sides. So 2a squared plus b squared plus 2 root 2 times ab is going to be equal to 3c squared. Okay, right, so that definitely means that we have to have either a or b. Therefore, a or b equal to 0. Because otherwise we can't cancel the root 2, else root 2 can't be accounted for or cancelled, accounted for, whatever way we want to think of it. So that started off there. So we've got, so we've already used that root 2 that they've talked about in the assumption, the little hint that they've put there. So a or b have to be 0. So let's say then if a is equal to 0, what are we getting? Then that means that we're getting that b squared is equal to 3c squared. So b squared over c squared equals 3, which can't be the case because root 3 is irrational. So that's not possible. So that would mean that we'd have to have b equals 0 and we'd have to have that c equals to 0. Right, so that means they're all 0. What if we had if b is equal to 0? Then we would have that 2a squared is equal to 3c squared, which again we can't have because 2/3 is the square root of 2/3 is irrational. That's used all three of the things that they've given us in the hint. So for the same reason, I won't write it out because I haven't got much space here as it is. But yeah, that all figures. So we've got 3 equations here, one with a root 2 in, one with a root 3 in, one with a root 2/3 in, and they're the 3 numbers that they've given us here in the hint. And we'll be showing that if we don't have all of a, b and c being equal to 0, then either root 2, root 3 or root 2/3 have got to be rational, which they're not. So that's good. That is a tough start for the first part of a long question. Throw that one in. That's not much fun. Right, suppose now that m and n lowercase, m and n uppercase are integers such as the distance from the point lowercase pair to root 2, root 3 equals the distance from uppercase pair to root 2, root 3. Show that m equals n, m and n equals n. Right, okay, right. So we're trying to show that there is only one point that has a particular distance from root 2, root 3. That's what it's saying. If you've got 2 different points, in theory, that are the same distance away from root 2, root 3, then actually there is only one point which is that far away. That's what we're trying to work out here. So how on earth am I going to actually do this? Right, let's pinch this space down the bottom, and then I'll just have to start a new sheet for subsequently. So the distance for one of them, so in the x direction, we'll have m lowercase minus root 2 squared. I'm just doing Pythagoras here, working out the distance between these 2 points. N minus root 3 all squared. That would have to be the same then for the capital letters. So capital M root 2 squared plus capital N minus root 3 squared. Don't think I'm going to have any option but to square these out, because we do need to get to show that these things are the same. So yeah, I think I'm going to have to. So m squared plus 2, then minus 2 root 2 lowercase m, plus n squared plus 3, plus, oh no, minus 2 root 3 n. We have exactly the same on the other side, but uppercase, m squared plus 2 minus 2 root 2 capital M, and then n squared minus 3 plus 3, minus 2 root 3 capital N. Right, so the 2's and the 3's are all going to cancel on both sides. So how on earth does this help? Like, seriously, how does that help? We've got lots of things with root 2's, right? This has got to be something to do with the previous part of the question, isn't it? Right, we can put it into that format, can't we? Because we've got stuff with root 2's, we've got stuff with root 3. So let's try and rearrange into that then. So what we got with root 2's, we got these two root 2's. So we got a root 2. We'll have 2m minus 2m, uppercase minus lowercase. So that has dealt with that term and that term. Okay. Then we want the bits that don't have any square roots in. So that's going to be an m squared and a n squared, and then minus the uppercase versions of each one of those. So that's dealt with that term, that term, that term, and that term. And then we've got the root 3 bits. So we're going to have a root 3 and then multiply, so that'd be a 2 lowercase n and a 2 minus 2 uppercase n. Right, so we've got that. I've got it into exactly the same format, and that means we need, so where, that means that 2m has to equal 2m, because that has to be 0. That's our a. This bit in the bracket here is our a, which we set out to be 0. And c has to be 0 as well. 2n equals 2n. Right, so m equals m and n equals n. Excellent. Right, okay, that dropped out a little bit easier than I thought it was going to be after I'd expanded out the brackets, because it did look quite unpleasant. Given real numbers a, b and a positive number r, let n, a, b, r be the number of integer pairs x, y, such as the distance between the points x, y, and a, b is less than or equal to r. Oh my word. Right, let's try and understand what's going on here then. We've got integer pairs x, y. Oh, for example, they've given an example. Right, I should have carried on reading. We see that n 1.2, 0, 1.5 equals 7. So A and B, are 1.20. Right, so that's where our center is of the circle at 1.20. And then R is the radius of the circle. Yeah, okay, so that circle is radius 1.5. And then how many? We've got 7. So this 7 is what? The number of integer pairs that are less than r. So it's the number of points inside the circle. 1, 2, 3, 4, 5, 6, 7. Right, there's 7 dots in the circle. If that is the center of the circle, right, so we're saying that is center of circle and that is radius of circle. Right, okay. So that's what they've got. And then the n is the number of dots. Right, that seems good. Explain why n 0.5, 0.5r is a multiple of 4. Right, so in this case, so 0.5, 0.5 is the center of the circle. So that's going to be there. It's going to be right in the middle of that little square of points. And then r for any value of r. So as r increases, right, well, this is equidistant from these 4 points. And then, so it'll hit those ones. We'll get to that point. It'll hit those. And then the next ones it's going to hit. What is the next one it's going to hit? Oh, good grief. Right, so it's going to be, well, it's the same distance away from that one and that one, and that one, and that one, and that one. So it's then going to hit those two, those two, those ones, those ones, those ones. So it's going to be that circle will be the next one, which has got 8 things in it. Yeah, because all of these are equidistant. All these dots are the same ones. Right, okay, so how am I actually going to turn this into words? So I need to turn this into, what do I need to turn this into? So we need to start off by saying 0.5, 0.5 is at the center of a square in, how am I going to describe this? It's like a lattice. It's like a dot matrix. Is the center of a square in the integer matrix of dots. I don't know how else to describe it. Integer matrix of dots, but that's what, or grid of dots, maybe, whatever you want to call it. But you've said it's in the center of a square. So moving outwards in all directions, we can say that we're going to get these integer pairs are going to be met in, well, they're not going to be met in batches of 4 necessarily. They're going to be met in batches of multiples of 4. But how are we proving this? I mean, I've shown it on the drawing. So in each, right, this is where we need to, I'm going to start a new sheet on this because, right, so I've set off this thing. Let's go back to this then. So we can say 0.5, I think I'm beginning to see how to put this together. 0.5, 0.5 is at the center of a square in the matrix of integer dots, or whatever I call them, integer dots. Right, so due to symmetry, this is, I always love anything which is due to symmetry in these maths questions. So moving up, down, left, right are all the same. And we've got lines of symmetry everywhere. I mean, everything is just lines of symmetry. So as R increases, we will encounter the same number of dots in each quadrant. That's where symmetry comes in. Same number of dots in each quadrant. So as in northeast, southeast, southwest, northwest. So therefore, we must have, n must be going up in multiples of 4. Right, therefore, n must increase in multiples of 4, which is what we want. Okay, that again was really tough. This is a rough question, this one is. Right, let k be any positive integer. Explain why there is a positive number r such that n root 2 root 3 r equals k. Right, this has clearly got stuff to do with what we've done already, because we've got this root 2 root 3 has come back in again. So if we've started at root 2 root 3, which is somewhere around about here, then we've said somewhere else, yeah, so this is coming back to part 2. So in part 2, we showed that there is only one point for a particular distance, k, there is only one point which is at that distance away from root 2 root 3. This is what we showed in 2. So yeah, that's exactly it. We don't have to even say anything more. So as shown in part 2, this is just seeing that you've understood what part 2 actually meant. There are no two integer points equidistant from root 2 root 3. Equidistant from root 2 root 3. So therefore, as r increases, dots are encountered one at a time, because we can't have one at a time, because if you encountered 2 of them at once, that means you've got 2 dots that are the same distance away from root 2 root 3. So let's just put that in. Else there would be 2 integer points equidistant from root 2 root 3. So we've got that as r increases, dots are encountered one at a time. So k increases by 1 each increment. Okay, that last part wasn't so bad for figuring it out because I'd already spoken about what part two was doing as we were doing it. I think that is a really difficult question, that one. And you might disagree, but I would say that's one of the tougher ones that I've seen so far. Admittedly, we're only on the 2010 paper, but I think that was pretty difficult. So well done if you got anywhere with that one, really.